Before we start talking about how to find the length of a circular arc, let's define what a circular arc is. Here's a circle. A circular arc is some portion of the circumference of that circle. So this pink curve on the edge of the circle is a circular arc. The length of a circular arc is usually called S, and it's believed this is either from the Latin spatium or possibly from the German Strecke. Now, I don't know either of those is actually the case, but it's a pretty good guess. A lot of mathematicians were German, and a lot of mathematical terminology is based on Latin. So it's not a definitive answer, but it's a question I've always had, and that kind of satisfies me a little bit. Now, if we want to figure out how long S is, there are, I suppose, a couple of different ways we could do it, but the way that it's conventionally done is by taking a look at the angle that goes between the two ends of the curved line segment. No matter how big that angle is, and I'm just going to call it theta here because that's usually what we do for angles. No matter how big that angle is, the amount of the circle that we have in this region here, the percentage of the circle, is the angle theta divided by the angle 2 pi, the whole circle. Let's compare that to the linear distance. So the angle theta compared to the whole circle is proportional to that portion of the circle that we're calling S divided by the circumference of the circle. Well, another way to write circumference is using its formula 2 pi r. If I cross multiply, I get 2 pi r theta is equal to 2 pi s. Divide both sides by 2 pi, and I get r theta equals s. That means that the length of this arc here can be computed if I know the radius of the circle and the angle. If you're someone who uses note cards, and I strongly recommend that you do, I certainly do, I don't have all of these things memorized. I would write this on a note card, S equals R theta, because that is a formula that you're going to be seeing and using over and over and over again in this class. Let's take a look at an example. Here's my circle, and I've been asked to find the length of the arc S. In the diagram, I've been given the radius, and I've been given an angle. So I should just be able to write S equals R theta and fill in the blanks. S equals R, which is 3, times theta, which appears to be 5 pi over 6. But I have to be careful because that is the arc for the angle 5 pi over 6. But look where it's labeled and look where it's highlighted. It's this arc here that I want. So I have to figure out what the angle is out here. I'll use pink. What this theta is, the one that starts here and goes around to there. Well, the whole thing would be 2 pi. So 2 pi minus 5 pi over 6. I have a common denominator of 6. So I have 12 pi minus 5 pi over 6. That gives me 7 pi over 6. And that's the angle that I need to use in my formula here. So let me change that to a 7. And now I can do the rest of my computations. The answer is that S is 7 pi over 2. Now again, we have to be careful because this looks like an angle measure. It has a pi in it. It looks like an angle measured in radians. But it's not. It's just that because the circumference has a pi in it, circumference of a circle is 2 times pi times the radius. The portion of the circle we're interested in, I should be using this diagram here, the portion of the circle that we're interested in is also going to have a pi in it. The length is going to have a pi in it. So this is my answer for the arc length of a circle with radius of 3 inches, the central angle of which we're interested in, which is 7 pi over 6. Again, I've had to be careful not to use the wrong angle. I was given a bit of a red herring here. I was given this angle, but it was this outside arc that was given for me to find. Something we have to be very careful of here is that the angles that I use in my formulas must be in radians, because the formula was derived using radians. If I use degrees, I'll get the wrong answer. Let's take a look at another example. Okay, in this problem, again, I'm asked to find the length of the arc S, and it's here, and the circle, the arc is highlighted so that we know which part of the circle we're interested in, and it's labeled S. It's this arc right here, and the angle, again, is given. This time it's given in degrees, and it's the inside angle, so this time they match. I don't have to go find the outside angle. I've just realized I haven't given you a radius here, but I'm going to go ahead and do that now. Let's call it 1 centimeter. And I've kind of chosen 1 here for this example because I really want to highlight what happens if you use degrees instead of radians. So I'm going to do this problem twice, but the first time I do it is wrong because I'll be using degrees. So my purpose in doing this is to show you why it's wrong and what happens if you do it this way so that you'll remember not to do it that way. All right, if I set up my formula, S equals R theta, then S is going to be equal to my radius, which is 1, times my theta, my angle, which is 90 degrees. It's not 90 degrees, it's pi over 2 radians, but we'll come back to that. So apparently, S is equal to 90. Okay, now let's do the same problem using radians. I'll put a dotted line down here. And the first thing I'll need to do is recognize that 90 degrees is equal to, well, let's not do it that way just yet. Let's go ahead and convert it. I have 90 degrees. I want to multiply it by 1. And I'm going to multiply it by the version of my formula that puts the degrees in the denominator so that my degrees will cancel. Then I can cancel my degrees, and I can also reduce my fraction. I get that 90 degrees is equal to pi over 2. So now, if I use pi over 2 in my formula, I have S equals R theta for my formula. So S is going to be equal to 1 times pi over 2. S equals pi over 2. That is approximately 1.57. Now, I'm measuring an arc length. This is called a linear measurement. Even though it's a curve, it's a linear measurement. We're kind of in 2 dimensions here, right? We're just walking along a line, a curved line. So either the length of this curved line is 90 or it's 1.57. In either case, it has to be in centimeters because that is the linear measurement we're using, right, in this problem. Now, 90 centimeters is clearly not the same as 1.5 centimeters. The other thing to note is that the length of this curved segment is some proportion of the entire circle. The entire circle has a circumference of 2 pi r. Well, r in this case is 1. So the whole circle here is, I'll write it, circle is 2 pi times 1, and 2 pi is 6.28. A small portion of that, 1.57, makes sense. 90 does not, right? This cannot have a length of 90 if the entire circle only has a measurement of 6.28. So that's one of the reasons that you have to use radians. This is the correct way to do this problem. And this is the wrong way, using degrees, okay? Don't use degrees. You have to convert. If you're given a problem in degrees, you have to convert it to radians first to use this formula. Now, the formula, which I've got written up here in the right-hand corner, top right-hand corner, if I solve this for r, I get r equals s over theta. So now I have it solved for s, I have it solved for r, and if I take the same original formula that I gave you there and solve it for theta, I get theta equals s over r. You don't need to memorize all of these. I know some of you will try to do that anyway, because you have the first one, right? All you need to do is take this one and solve it for whatever variable you need. The reason for doing that is that in this version, I can take a circle whose radius I know and the central angle I'm given and use that to find the length of an arc, right? So if I'm given the angle and I'm given the radius, I can use this formula to find the length of the arc. If I'm given the arc and the angle, I can use this formula to find the radius. And if I'm given the arc and the radius, I can find the central angle theta. This is really the only one you need because you can derive these other two very easily from this first one. But notice that just like any algebraic formula, if you have two of the three pieces, you can find the third depending on which sort of version of the formula that you use. So in this video, we've been talking about this circular arc here, this portion of a circumference, which we call an arc. And we've called this thing in the middle here a central angle because it's centered. The angle as its the common endpoint of the rays is the center of the circle. So it's a central angle, and it's the arc we've been interested in. In the next video, we're going to be talking about how to find the area of this whole region here, which is called a circular sector.